So in the first part of Zinc-Air battery description, we have focused our attention on the general structure, the general aspect, the main important advantages, and also the most important problems concerning the possibility to develop a secondary battery, Zinc-Air battery. And we have focused basically our attentions on the anodic problems. And so, for instance, the passivation, the creation of insoluble film oxide, fighting the diffusion of OH- as a product of these reactions toward the anode. We have focused our attentions on the problem of the bad redeposition, with even the possibility to close the circuit, breaking down the separation membrane and cause short circuit. And we have described, according to the Purbe diagram, basically the possibility to involve side reaction, and so the corrosion of the electrode, losing zinc, promoting the evolutions of hydrogen. But we have described how, working in superalkaline condition, we are promoting the formations of zincate, and so synthetically fighting the generations of hydrogen, even if from a theoretical point of view is promoted in thermodynamics. So basically, in this case, what is important to say is that we have focused our attentions on the anodic problems, but we have even some problems concerning the cathode and the electrolyte. So how we can see, even if the Zinc-Air battery are extremely promising, because are lighter and can store a lot of energy, this is a great potentiality, we have a lot of problems. And so these problems are concerning the anode, but for what concerns the cathode, we have, for instance, the fact that how we have described in the first video, speaking about, in general, about metal in the battery, we have described basically how, since we are taking oxygens from outside, that means that in all that situation, even if we are saving weight in which oxygen is purely present, we have difficulty in achieve our function, and the battery can't work. And also another aspect is that when we are exploiting the high current, since the fact that oxygen is taken from outside, we have problems in the diffusion and we have huge overtension involving mass transport. So another aspect that is interesting is consider what is the structure of a GDE before start speaking about the problem of the cathode. And so the GDE basically stands for gas diffusion electrode. It is a part of the electron membrane assembly, for instance, in fuel cell, but we will see this speaking about fuel cell. So the gas diffusion electrode is a particular type of electrode that is able to allow an homogeneous diffusion of oxygen toward the catalytic side. And so, in fact, the gas diffusion electrode is composed as the sum of a gas diffusion layer and a specific catalyst. So the catalyst is actually the side in which the reaction, the oxygen reduction reaction, or if we want to design a secondary battery, both the oxygen reaction, reduction reactions and the opposite one, the oxygen evolution reactions, can be realized. So it's the place in which the reactions occur, oxygen reduction reaction and eventually even oxygen evolution reaction. And the gas diffusion layer that is able to promote an homogeneous diffusion of oxygen. And from a real point of view, we can say that the gas diffusion layer is a carbonous material. It's a carbon material in order to ensure a certain conductivity. And basically we have that is composed often as a woven of carbon fibers in a specific carbon clothes, or even could be created due to pressed carbon fibers in a carbon paper. And some obviously is created in order to ensure a microporous aspect. It seems to be smooth, but with a huge surface area in order to maximize the diffusions and also the interactions with the electrolyte. And sometimes we can even appreciate inside the functionalization, or not functionalization, but the use of basically Teflon, tetrafluoroethylene has a binder, because in this way we are improving the hydrophobicity. So we are using something that is carbon-based, but with something that is polymeric-based as binder. Teflon, really hydrophobic. Let's imagine how much remembering the contact angle of water, for instance, of Teflon. Teflon is a typical case of super hydrophobic surface, since water is rolling down without penetrating this material. And this is extremely important because we want to tune the management of water. What does it mean? That we remember that in, for instance, Zinc-Air battery, but also in fuel cell, the electrolyte is water-based. And so what does it mean is that we need to ensure from one side the passage of oxygen, but from the other side avoid the evaporations of water, the asking of water from the electrolytes towards the pore of the gas diffusion electrode. And so in this case, the gas diffusion layer should be made even with a component that is hydrophobic, Teflon. And sometimes you can even have a real external Teflon membrane. So we have something that is able to promote the conductivity, to promote the diffusion and the hydrophobicity, and we have something that can catalyze the reaction. They are pressed together, closed, and with a specific collector, often is a metal woven, a metal ring, something that can act as a current collector, we are able to create our gas diffusion electrode. So this is the structure, basically, of our gas diffusion electrode. We will see how much important is, for instance, in fuel cell, in which we are using hydrogen and oxygen, for instance, in order to create electricity in a sort of green process that has, as a result, only a product that is water, so a green process. So we have defined, so since here we have the diffusions of oxygens from outside, which are the problems concerning the use of these types of electrode, but we can even have, since this is a porous structure, sometimes the evaporations of water, so a little bit amount of water can ask from the pore of the GDE. And so we can have the concentrations of the electrolyte with changing in viscosity and the conductivity that can cause the problem. From the other hand, we have quite in a precise way described already this in the first lesson speaking about the metal air battery. We have the diffusion of CO2 from outside, since also CO2 is present in the atmosphere, that can create carbonate and bicarbonate, characterized due to the interactions of these inside water that are able to promote the clocking of the pores, maybe can, when we have an high concentration, generate sedimentations. But more important is the fact that these ions are less mobile with respect to this one. And so we are basically decreasing the performance of our battery. Or even in moisture situation, when maybe we are under rain and something similar, we can even have the introductions of water inside. Obviously we have binder, we have a Teflon binder trying to minimizing this effect. But maybe we can have a certain little amount of water that can penetrate, and in this case we are diluting the electrolyte and we are against generating problems in terms of conductivity. So we have problem of dilution, we have problem of concentration due to the evaporations of electrolyte, so the two opposites problem, movement of water from inside to outside and from outside to inside. In both these two cases we have a problem. The interactions of CO2 with the carbonylation, the generations of due to the reactions of these and water carbonates and hydrocarbonates, and the problem concerning the overtension. So basically we have a lot of different problems also for what concern the electrolyte and the cathode. Now what is important is remember that there are different types of metal Zinc-Air. For instance, in industry we can have a Zinc-Air battery exploiting the use, for instance, of a tank of calcium oxide. Calcium oxide is used because it has a double effect. The first one is to react with carbonates and to carbon dioxide in order to avoid the decarbonization effect, and also react with the soluble product of the zinc oxidations, avoiding a bad reposition mechanism. And we can even have a second tank trying to correct any types of changes in water and concentrations in the electrolyte due to evaporation or dilution. And also we have, for instance, sometimes the possibility to exploit the hybrid zinc-air oxide manganese battery, in which together with the gas diffusion electrode we can have some manganese oxide that is able to ensure the working of the battery even if we are in condition in which oxygen is purely present. So it's basically a zinc-air battery, but when oxygen is not able to supply sufficient matter in order to ensure the workings of the battery, we have the reductions of the oxide with respect to oxygen. Obviously it's important, I don't remember if I stressed it sufficient this aspect, but the catalyst, the point which the oxygen reduction or eventually the oxygen evolution reactions occur, is made of cobalt oxide, magnesium oxide, or some noble metal often. So then it's important to remember that for what concerns the rechargeability of a zinc-air battery, we have two different steps of rechargeabilities. The first one is a conventional standard approach, so we're applying a potential, transforming our cell in an electrolytic cell, what we have described before with the connected problems of redeposition, of corrosions, and all the other aspects that we have looked basically in these and in the previous lessons. But we can even have mechanical recharging. What does it mean? Basically, if we are looking about particular types of design zinc-air battery, we can have, for instance, a single metallic zinc electrode and two different, so this is, for instance, the negative electrode, this one that is colored, that is the one in which zinc oxidation is occurring, and we have two different cathode, two different positive electrodes in which oxygen reduction is proceeding. Nothing different with respect to the previous situation, but in this case we have only one negative electrode and two positive electrodes are separated with an ion permeable but not electron conductive membrane. What does it mean? That when we have consumed our zinc, so when our zinc it was totally, or at least for the major part, completely converted in zincate, and so the zinc-air battery is approaching its die, we just needed to substitute this electrode with a fresh one with new zinc. And so in a specific process we are able to represtinate the workings of the battery just removing one of the two electrodes. So it's not a real recharging, so it's not a recharging in a conventional way by applying a potential, it's not a recharging due to the applications of a current, it's a recharging due to a mechanical action. But it's a smart way in order to overcome the all difference problem connected with the battery deposition mechanism, even if obviously we are wasting money and matter since we needed to replace the zinc electrode.